All right, 3PN4 students, we're continuing our coverage on the junction transistor. We already introduced the bipolar junction transistor, and just as a very quick review, we have a situation where a PNP transistor looks like that. In this case, holes are injected from the emitter through a base and into the collector. And the base essentially is a region in which the holes diffuse. And the diffusion of holes really relies on the holes not recombining. And so the base is made as narrow as possible, and in that way we can minimize the chance of recombination. So what will happen in this device is the current is flowing. We want to minimize recombination in the base. We have equations which relate to that. Just give me one moment. And we're going to now look at the model by which we can represent some parameters to explain the degree of recombination in the base, and also the degree to which base current would flow in the transistor. Remember, we're trying to minimize the amount of base current that flows. So the first parameter we want to look at is the base transport factor. And the base transport factor we call B, and we define B as IP of WB divided by IP at 0. So what this means is that within the base, which extends from 0 to WB, we have a concentration of holes, delta P sub n, and that concentration of holes falls off with a change in slope from the one side of the base to the other side of the base. So the slope here, which can be used to calculate the current flowing out of the base, is compared with the slope here representing the current flowing into the base. So that ratio is what we call the base transport factor. And of course, the best possible value of B would be 1. And in a real transistor, B is always less than 1, but hopefully not much less than 1. In ways in which we can maximize this parameter, by minimizing scattering. So remember, we want to maximize the diffusion length L, P, equals square root dP tau P. So if you minimize scattering, that means we can cause tau to become longer. The time between scattering events can become longer, which will increase the length L sub P. And we can, of course, also reduce WB. Practically speaking, there's a limit to how much we can reduce WB, because as you make the base thinner, you will also increase the resistance. So if you're trying to make an electrical contact to the base, the electrical resistance through that base region will actually go up. So there's some interesting practical limits to how narrow you can make the width of a base. And you can now use these two techniques to make B as close to 1 as possible. Now there's another important parameter. And this parameter is called the emitter injection efficiency. So remember, at the emitter base junction, we have the situation where excess holes can be injected into the base, and excess electrons can be injected into the emitter. So X sub B is really X sub N because the base is N type. X sub P is the emitter, which is P type. And we have excess electrons being injected into the emitter, excess holes being injected into the base. By heavily doping the emitter P plus and the base not so heavily, we can increase the supply of minority carriers into the base and minimize the supply of minority carriers into the emitter. Nevertheless, this is never going to be perfect. We'll always have some carriers injected into the emitter. And so we define the emitter injection efficiency gamma that equals IP of 0 divided by IP of 0 plus I sub n. So what this means is the emitter injection efficiency is the injection of holes, the hole current at 0, which is defined by the slope at the beginning of the base, divided by the hole current at 0 plus the electron current, which represents electrons being injected into the emitter. So that should be, again, as close to 1 as possible. And practically speaking, if you had a 100 times bigger doping in the emitter compared to the base, you could get on the order of 100 times higher hole current compared to the unwanted electron current, in which case gamma could be about 0.99, and that's a typical value of gamma. So now, of course, to figure out how good the transistor is, we need to know not just gamma, we also have to know what B is, which is the base transport vector, the current flowing out of the base relative to the current flowing into the base. So we actually define a new parameter we define alpha, which we call the current transfer ratio, and that value of alpha equals IC over IE, and it's defined as B times gamma. So it's now the product of the base transport factor times the emitter injection efficiency. And so if each one of these terms approaches 1, then alpha can also approach 1. So let's see what the total base current is now. The total base current, which we'll call I sub V, is equal to I sub B plus I sub N. This represents the base current which flows due to recombination. So remember that inside the base, the charge in the base, which is the area under this curve, is the charge in under that curve is really recombining in average time tau, the recombination time, which means that the base current that flows is due to the loss of carriers in the base. And that loss of carriers can be expressed as 1 minus b times ip of 0. In other words, this is ib of 0 minus ip of wb. So it's the base current flowing in minus the base flowing out. And that difference will represent the base current, which is the recombination within the base. And I'm going to then add I sub n, which is the other source of base current, which is base current that leads to the injection of electrons into the emitter. Both base currents, incidentally, flow in that direction, because current flow this way means electrons injected into the emitter, and it also represents the recombination of holes in the base as electrons enter to resupply those holes. So we're now going to take this and add I sub n to it. So we have an expression here for the base current. Once again, a recombination term in the base, which is all this, and then this other term, which is the supply of electrons into the emitter. Now, we define another parameter, which should be familiar to you if you've ever used a transistor or looked up a transistor in a manufacturer's spec sheet. This parameter is called beta, which is the most widely published parameter for a transistor. It's the collector current amplification factor. And we define beta as I sub c divided by I sub b. So it's the collector current that the transistor can sustain for a given base current. And we can write that as b ip of 0. So the collector current is the base transport factor multiplied by the current entering the base. And we can divide it by ib, which is this expression over here. Okay. So we're now going to simplify this expression. So we're going to take this expression and we're going to divide the numerator by ip of 0 plus in, and we're going to take the denominator and divide it by ip of 0 plus in. So far all I've done is I've divided both numerator and denominator by the same expression. And I'm now going to rewrite the numerator. If you go back to the previous section of this video, you'll see that we defined gamma as that ratio. So you can see the numerator here is really just b times gamma. The denominator I'm going to rewrite as, I'm going to group these terms. We have an IP of 0 plus IN, so there's going to be a 1. And then the remaining term will be IP of 0 divided by IP of 0 plus IN times B. So you can see that the denominator can be written 1 plus B gamma. Sorry, I'm losing my position on your camera. So we've got B gamma over 1 minus 1 plus B gamma. And I can rewrite that as alpha divided by 1 plus alpha, because we have this relationship, alpha equals B gamma. So this becomes the relationship to define beta. Now beta is a number which is going to be quite large, because if alpha is almost equal to 1, let's just say for the sake of argument that alpha is 0.99, then this ratio could be approximately 0.99 divided by 0.1, 0.01, which equals 99. So you can see that our value of beta would be more like on the order of 100. So a good transistor would have a value of beta on the order of 100, perhaps between 10 and 100, depending on the application and the type of transistor. And very typically it could be 60 or 80 or 50. So beta values tend to be in the range 10 to 100. Now, then there's a lot about a transistor we haven't covered yet in this course, and I just want to mention a couple of interesting aspects of a bipolar junction transistor. We had described the actual physical manufacture of a PN junction, and I just want to give you a quick idea of how a bipolar junction transistor would be manufactured. So unlike the very first transistor, which was invented at Bell Labs in the 1950s, the idea of planar processing became a dominant theme. And I mentioned this before in the context of diodes. We had one of the 3 Nobel Prize winners at Bell Labs, Shockley, William Shockley. He founded his own company in California, the Shockley Semiconductor Company, and they started making bipolar junction transistors out of germanium, and they were able to commercialize the transistor for the first time. And the people who worked for Shockley found him very troublesome to work for, and they founded their own company called the Fairchild Semiconductor Company. And their big innovation was planar processing. And we described the PN junction as a device where you would, for example, take a p-type silicon substrate and create an n-type region in the substrate by a diffusion process, and that n-type region would form a PN junction by putting ohmic contacts on the 2 different semiconductor regions. Of course, you could also reverse this, and you could create a p-type region in an n-type substrate. Well, it doesn't take much imagination to extend this into the formation of a bipolar junction transistor. So I could take a p-type substrate, I could create an n-type region, and then I could do a second diffusion step and reintroduce n-type dopant into that structure and create an n-type region. So I could do an initial diffusion where I diffuse p-type dopant in, oh sorry, let me try this again. So start with a p-type substrate, we introduce an n-type dopant, and then we introduce a second dopant, which would be a p-type dopant. So you can see we've created a p-n-p structure, and if you were to look from the top to the bottom, I'm going to sketch the doping profile. So first I'll sketch the profile of the donors in this device. We have Na, which is the substrate doping. That means that the substrate itself is a uniformly doped p-type material with an acceptor doping level of N sub A. Now we diffuse in an n-type layer. So this is now Nd. The donor concentration falls off according to the doping profile, and at a certain point there's a crossover between donor and acceptor doping. So on this side of the line we would say it's p-type, and on this side of the line we'd say it's n-type. Then after this doping is complete, we introduce this second p-type layer. So we're now going to introduce an acceptor doping again, but only near the surface. So we have a very high concentration of acceptors near the surface, which falls off according to the doping profile. In principle, we would reduce the diffusion length in the p-type doping by reducing the length of time and or the temperature of the diffusion of these impurities. So now what you can see is there's going to be another p-type region at the surface. So actually the surface region here has two sources of p-type doping, both from the substrate and from this high concentration diffused source. And it also has one n-type dose of doping, but the n-type doping is overwhelmed by the p-type doping, so it becomes a net p-type. So now with this structure you can put electrical contacts onto these three regions, which become the collector, the emitter, and the collector, the base, and the emitter. And you can see that the emitter is naturally going to be heavily doped, which is what we want because it's right near the surface of the transistor. And that gives you the high emitter injection efficiency. That means high hole flow relative to a low electron flow in the base. The base layer has a certain level of doping, not too high and not too low. The collector region has a relatively low doping level, which is good because the collector base junction will have a reverse bias. And we want a relatively high breakdown voltage for the collector base junction. The breakdown voltage depends on the doping level, so we don't want too heavy a collector doping to get a relatively high breakdown voltage at the collector base junction. If you were to look at the front view of this, or the top view of this device, it might look like this. So you can see that the base might look like a sort of donut region, and you could put the base electrode all the way around this donut. So this could be metallized in a circle, and then you could connect the base lead to that circle which connects to that entire ring of base material. The emitter contact pad here would have a connection to it, and then the collector could also have a circular ring-type conductive layer, and then you could connect to the collector as well. So that's a very simple, very straightforward donut-style bipolar junction transistor, all planar processing, so you can create thousands and thousands of bipolar junction transistors on one smooth silicon wafer. Very cost-effective, and a revolution in electronics which occurred in the 1960s. Now, one thing that I should mention is that this type of transistor, great as it may be, is not the transistor that's used in high-density microelectronics today. The transistors that people use are called MOSFETs, and although this can be made small, a MOSFET can be made much, much smaller than this. So in fourth year, I think you'll have the opportunity to study the MOSFET in detail. Just keep in mind that these bipolar junction transistors are still manufactured in high volume for many, many applications. Now, the very last section of this chapter on the junction transistor is devoted to the junction field effect transistor. So the junction FET is a device that's rather simple. It's actually simpler to understand than the bipolar junction transistor. And we can start our discussion of the junction field effect transistor as follows. The junction field effect transistor consists of a P plus layer, an N layer, and then another P plus layer. By the way, I should mention before I forget that both for a junction FET and also for the bipolar junction transistor we just finished talking about, you can always reverse the P and N. So you can create a PNP bipolar junction transistor, you can create an NPN, and in the case of the JFET, you can create a JFET like this, or you could also create a JFET in which the middle layer here was P-type, and the top and bottom layer was N-type. So the principle of operation of a JFET is that the current that flows through the device flows through this N-type layer, in this case, from what we call a source with the letter S and a drain D with the letter D. And the way in which we control the flow of current from the source to the drain is by varying the thickness of this N-type layer. So the thicker the N-type layer, the more current can flow, the lower the resistance through the N-type layer. And the thinner we make this N-type layer, the higher the resistance and the less current would flow from the source to the drain. So we call this the channel. So it's the channel through which current flows between source and drain. And the thickness of this channel is very simply controlled by varying the depletion width of the depletion regions between this P plus layer and the N layer. So you can see there are two depletion regions on either side of this channel, and you can vary the width of those depletion regions. And the way you would vary the width of the depletion regions is by varying the voltage across this PN junction and this PN junction. So we would normally connect this PN, this P region over to this P region so that they are connected to the same voltage, and we would call that voltage V sub G, and G stands for gate. So by varying the voltage on the gate relative to the voltage on the source, you can control the widths of these two depletion regions, and therefore you can control the remaining channel width through which the source drain current is passing. So we're going to ground the source. We're going to put 0 volts on the source as a reference point. And so you can see VG will now determine the bias voltage across this PN junction and across the next PN junction. Well, we know from previous chapters that the width of the depletion region is approximately given by this expression. So if you go back to chapter 3, you'll find an expression for the width of a depletion region. Now in this case, we've intentionally doped these regions P plus because we want the depletion region to extend mostly into the N-type layer, because that's how we vary the width of the channel. Extending the depletion region into the P plus regions is not helpful to us. So heavy doping in the P regions means that approximately the width of the depletion region is only dependent on the N-type doping, which is ND, which is the doping in the channel. So once you have the width of the depletion region, we can now express the channel width. So the channel width is a function of V sub G, which is the gate voltage, and it's going to be H minus 2W, where we define H as this. H is defined as the metallurgical junction position here relative to the metallurgical junction position there, the two metallurgical junctions. Once you subtract the depletion regions from those, assuming W is really virtually all in the N layer, you can neglect the small amount of W extending into the P layer, and you can approximate that the height of the thickness of the channel is H minus 2W, which equals H minus 2 square root 2 epsilon naught epsilon R times minus VG over Q and D. Now, something interesting happens, because if you continue to make the negative voltage minus VG more and more larger and larger, of course, the minus sign makes this a positive number because you can't take the square root of a negative number. So VG is negative, minus VG is a positive number. As you make that number larger and larger, eventually H will approach 0. So you can reduce the channel thickness to 0, and we call that condition pinch-off. So you can pinch off the channel with a sufficiently large reverse bias between this P region and this N region. And at the point of pinch-off, the condition of pinch-off is reached when Vp is equal to Q ND H squared divided by 8 epsilon naught epsilon r. So in order to obtain this expression, what you would do is just substitute H minus 2W equals 0. So to get this expression here, H minus 2W equals 0. So therefore W equals H over 2. If you substitute H over 2 into the expression for W, you plug H over 2 into there, you will get this expression and solve for the pinch-off voltage Vg. So the interesting thing now becomes what happens at pinch-off. If the channel width is 0, what happens to the current flowing between the drain and the source? So let's see how the current flow depends on the voltage you apply to the gate. Okay, now, what's happening here is that the drain current is the current flowing through the channel. So this is where current can flow from the source to the drain. And of course, the resistance of the effective resistor that exists between the source and the drain depends on the thickness of this channel. So the resistance actually determines the slope of the drain current versus the drain source voltage, because you can think of this as a resistor connecting the source voltage to the drain voltage. So if you model this as a resistor, then we should get a straight line relationship between the current and the voltage through that channel, and you can represent it as a resistor. And if you were to increase the gate voltage, the depletion widths would get wider and the resistance would get higher, and you'd get a reduced slope. And if you increase the gate voltage more, the resistance would get even higher and you'd get an even more reduced slope. So an example could be that this might be Vg equals minus 4 volts. This could be for Vg equals minus 3 volts. Vg equals minus 2 volts. Vg equals minus 1 volt. And finally, Vg equals 0. So we're changing the slope of that resistance, which is the channel, depending on the thickness of the channel. What's interesting is that you can reduce the conduction through the channel down to virtually nothing by increasing the gate voltage to the point where you have pinch-off. So in this transistor, this particular transistor, minus 4 volts represents the pinch-off voltage on the gate. Now, something rather interesting happens when you use this device because on the x-axis I have the drain to source voltage. And so far we've assumed that the drain to source voltage is a very small value. But if you increase the drain source voltage, which is effectively like increasing the voltage across this resistor, you would expect the current to rise in a straight line, which is Ohm's law. But what you'll find is that the current will saturate. And what's happening is that on the drain side of this device, the voltage drop between the gate and the channel depends on the voltage at the drain. So that's a very different situation. You can't expect the drain side to behave the same as the source side. So as the drain voltage goes more positive, the channel is going to pinch off, move toward pinch off on the drain side. So if you were to look at the device over, let's say, there, if I took a picture of the channel in this operating point, what you see is that the channel has pinched off. So the depletion widths on the drain side of the device are wider now because we've made the drain voltage more positive compared to the source voltage. So this is the source, this is the drain. As the drain voltage goes more positive, the reverse bias across the NP plus region becomes higher. You get a stronger reverse bias. The stronger reverse bias means that the widths of the depletion region on this side are higher than the widths of the depletion regions on this side, which means that the channel is shaped like a wedge. And the channel can reach pinch off on this side. And that pinch-off can occur on one side only. And when pinch-off occurs, the linear relationship which we established for low values of VDS becomes nonlinear, and you start having what's called saturation. This is called saturation. And in saturation, the current between the drain and the source no longer depends on the voltage across the drain source. So what happens is you can change the voltage across the drain and the source, and what you will do is you'll move the pinch-off point from near the drain, and you'll move the pinch-off point inwards towards the source. So if I go to a higher operating point like that, at this operating point, the device would look more like this. So what you'd see now is that the channel would pinch off not at the drain, but well before the drain. So pinch off there at the drain, pinch off here well before the drain. So actually, this point here, where I drew the original pinch-off condition, should have been more like there. And then as I move along this curve, that pinch-off point is moving to the left, and the pinch-off point is moving to the left. Interestingly, although the channel's pinched off through this entire length here, the current is still flowing. So that pinch-off will not stop the current flow. It'll simply prevent it from increasing. So it's like taking a river and squeezing the river into a very narrow channel. And you can't cut the current off, and you'll find that there's a very skinny flow along a virtually infinitely thin channel, but you don't lose the current flow. The current continues to flow through the device. So the characteristic curves of a junction field effect transistor look like this. And the question is, what's the real significance of a junction field effect transistor compared to a bipolar junction transistor? First of all, the junction field effect transistor has an important advantage. It has essentially zero gate current. If you remember, in the bipolar junction transistor, the current flowing into the base could give rise to a collector current, which was perhaps 100 times bigger than the base current. Whereas in the junction field effect transistor, there is virtually no current flowing into the gate. The gate is a reverse biased PN junction, and in reverse bias, you know from chapter 3 that the current flow is I0, which is extremely small. So you would expect virtually no current flow into the gate. That means that you can regard the JFET as a virtually infinite input impedance device. And that has benefits if you're trying to detect voltage, to build an operational amplifier, to detect very, very weak signals. Those very weak signals can be detected without demanding current from them when you're trying to amplify them. On the other hand, a bipolar junction transistor is very robust and rugged, and it has important applications where you're trying to get high current output and behavior that's really dependable in a wide range of adverse conditions, such as noise and voltage transients, etc. It's a more robust device than a junction field effect transistor. I just want to mention one other final point. The characteristic curves of a JFET are sketched here. So I'm going to resketch the characteristic curves of a JFET, and then I'll contrast those with the characteristic curves of a bipolar junction transistor. So here are some of the curves for the JFET that I sketched just now. And you can see that the saturation regime exists, and you've got the linear regime down here. In the linear regime, the channel looks like this. So we can consider the channel to be virtually parallel with not much change in width from one side to the other at these very low voltages. So that's a linear regime. As you get to the pinch-off regime, the channel width starts to pinch off. Okay, now let's look at a bipolar junction transistor and the way the current voltage behavior looks. So in a bipolar junction transistor, if I put a certain base current in, let's just say a base current of 0.1 milliamp, and let's assume that the current amplification ratio was 100, I would expect to get approximately 10 milliamps of collector current. So this is for beta is equal to 100. The 0.1 milliamp base current should give rise to about 10 milliamps of collector current. So you get this curve here until you reduced the collector emitter voltage to a very small value. So you get a saturation effect in a bipolar junction transistor. And of course, what's going on there is that the base current is what's recombining in the base plus what's being injected into the emitter. And that same situation keeps going regardless of how big the collector emitter voltage is. And you can view that by looking inside the base. So we have, within the base of the bipolar junction transistor, we have a certain amount of charge Q, which is flowing, which is stored in the base, and this charge gives rise to the diffusion current through the base. Now, if I change the value of the collector emitter voltage, what am I actually doing? What I'm really doing is changing the width of the depletion layer between the base and the collector. And that depletion layer width will have some effect on the width of the base. So in other words, at a high voltage, I get a slightly narrower base, and at a low voltage, I'll get a slightly wider base. So there will be a small change in the slope of this excess carrier concentration in the base as I change the depletion width at the base collector junction. But nevertheless, I won't significantly change the depletion width. I won't significantly change the conditions in the base as I change the collector emitter, the base collector depletion width. The assumption is that depletion width mostly extends into the collector and doesn't extend so much into the base. So the base width is relatively insensitive to that collector base depletion width. So you can see why you end up with a saturation condition. That condition exists because the current flowing into the collector is determined by the slope. And the slope of this excess carrier concentration in the base is controlled by the emitter base junction. If the emitter base junction is not affected by the collector emitter voltage, then this current would just remain relatively saturated. So now if I want to change that current, I could go to a different base current. And as you can see, I can get different values of collector current depending on the base current. So in both types of transistor, it turns out that you get saturation behavior for significant values of collector emitter voltage in the case of a bipolar junction transistor, and significant values of drain source voltage in the case of a junction field effect transistor. So what I'd encourage you to do is to read Chapter 8. I've tried to summarize the important parts of Chapter 8, but it wouldn't hurt you to read the whole chapter. I've given you 4 homework problems in Chapter 8, and I will include these concepts on the final exam. I will say goodbye to you now. I will definitely stay in touch with you throughout the rest of the semester. I'll be checking my emails regularly, and I'll be happy to answer all your questions. Keep tabs on your due dates, etc. And I wish you all the best for your final exam.